Okay, so in this video, we want to review how to add fractions together. So let's assume that a, b, c, d are positive integers. And what if we want to add a over b with c over d? So here's the result. And if you remember, this is sometimes called cross multiplication, right? We do a times d plus b times c and over b times d. So it forms kind of a bow, right? AD plus BC on the numerator, and on the denominator, b times d. So let's see why this makes perfect sense. So let me start over with a over b plus c over d. And again, the idea is to think of each fraction as breaking down, and again geometrically, a circle into, in the first case, b parts, and in the second case, d parts. So inherently here there is a problem, right? If you start with a given circle, and in the one hand, you divide the circle into b parts of equal size, and on the other, you divide the same circle into d parts of equal size, if b and d are different, then the pieces are of different sizes. So here you have A pieces, here you have C pieces, but the pieces here are different than the pieces here. So the idea is you have to break down the pieces in each case further so that they end up with the same size. So, how do we do this? Well, the idea is to multiply each fraction by 1. So in the case of b, we're missing a d. So we multiply the first fraction by 1, simply taking d over d. Right? This is equal to 1, so this will not change the original fraction a over b. Plus, and in the case of c over d, well, the d here is missing the b. So we multiply the second fraction by b over b. And once again, b over b is 1, so we are not changing the second fraction. And we've previously reviewed how we can multiply fractions, right? We simply multiply the numerators together and the denominators together. So we're going to get AD over BD for the first fraction, and plus CB over DB. And now if you look, in both cases, we are over BD, the same denominator, right? BD or DB, this is the same thing. So now in both cases, we are taking a given circle, splitting it up into BD many parts. So now all the parts are of the same size. So here we have AD parts, here we have CB, which is the same as BC parts, and because of the parts are of the same size, we can simply add them up together. So we divided up a circle into BD parts, and we're adding up the AD parts with the CB, or in this case BC parts. So you can only add two fractions together if they have the same denominator. Simply put, you can only add pieces if they are of the same size. So let's look at a very simple example to illustrate why it is crucial that when you're adding fractions together, you have to have the same denominator. Let's take a very simple example. So we have a circle as a whole. So what if we wanted, say, to perform 1/2 plus, say, 1/3? And we ask, what is this equal to? And this will illustrate why, when you have different denominators, why the pieces are of different sizes. So 1/2, we split the circle into two pieces of equal size, and we take one of them. So this is our 1/2. In the other case, we divide the circle now into three pieces of equal size. And we take only one of those pieces. So you see, we can't just say, well, this is 2 over something, because this piece is much larger than this piece. So what we have to do is cut each circle into more pieces so that the pieces are of the same size. So the idea now is to subdivide each half of the circle into 3 parts of equal size. And thinking of why are we doing this? Because the least common multiple of 2 and 3 is 6. If we sort of cheat here, over 2 over 3, so the result should be over 6. So if we divide now each half into 3 parts of equal size, and divide now each third into 2 parts of equal size, we haven't done anything. This is still 1/2, this is still 1/3. But now we have a smaller partition of each circle. And if you look, 1, 2, 3, 4, 5, 6 pieces of equal size. 1, 2, 3, 4, 5, 6 pieces of equal size. So now, having broken down the circles further, we can perform the addition. So 1/2 viewed into 6 many pieces is 1, 2, 3 out of 6. And 1/3 is viewed as 1, 2 pieces out of 6. And now we can perform the addition, right? Over 6, the pieces are of the same size. So we have here 1, 2, 3 pieces, plus 1, 2. So we have, of course, a total of 3 plus 2 over 6 pieces. So we have 5 out of 6. And of course, the 3 over 6 was obtained, thinking of our trick here, by doing times 3 over 3. As again, this is 1, and here by doing times 2 over 2. 1 times 2 is 2, 1 times 3 is 3, 2 times 3 is 6, 3 times 2 is 6. And this is why, before you can add 2 fractions together, you have to put them under a common denominator, which means geometrically that you're splitting up the 2 holes, the 2 circles, into pieces of equal size, and then they can be added up together. Let's look at 2 more examples, and again, we will always use this trick, as this one is a little lengthier. So when you're adding fractions, we simply do a cross product, AD plus BC over BD. So here's our next example. What if we wanted to perform, say, 2/3 plus 7 over 10? So 3 and 10 don't share any common factor. They're obviously different. So what are we going to have? Well, 2 times 10 plus 3 times 7 over 3 times 10. And if we simplify, 2 times 10 is 20, plus 3 times 7 is 21, over 3 times 10 is 30. And if we add the numerators, we get 41 over 30. So 2/3 plus 7/10 is 41 over 30. Let's look at one last example to show that we have to be a little careful at times before pulling the trigger when we're adding fractions, and not simply doing the cross multiplication. And this is the case when the denominators share a common factor. So to illustrate this, we will first present a wrong solution of the addition, then present a better solution of the problem. So what if we wanted, say, to add 7 over 10, as before, but now plus 5 over 12? So again, this will be the naive solution, where we're going to work a little too much. So we perform the cross multiplication, 7 times 12, plus 10 times 5, over 10 times 12. Multiplying things out, 7 times 12, well, we get 70 plus 14, so 84, plus 10 times 5, 50, over 10 times 12, 120. Let's perform the addition on top. 8 plus 5 is 13, that's 130 plus 4, 134. over 120. And this is our answer, but we can do a little better, right? In the previous example, 41 and 30 did not share any common factor, so this fraction was already fully simplified. But if you look, obviously 134 and 120 share a common factor of 2. They're both even numbers. So if we factor 2, well, 2 times what is 134? This is 67, right? 2 times 60 is 120. 2 times 7 is 14. 120 plus 14 is 134. And obviously, 120 is 2 times 60. We can cancel 2. And so the reduced fraction is 67 over 60. So if you perform 7 over 10 plus 5 over 12, the answer is 67 over 60. But this, I claim, is a rather lengthy solution. So now let's perform the addition, but let's be clever about this. Why wait until the very end to cancel a common factor of 2 when we should have factored this right from the beginning? As it's easy to see that 10 and 12 share a common factor of 2. So here's now the better solution. Noticing we have a common factor of 2, we can factor it as 1/2. So this will be 1/2 of. Well, if you factor 2 from 10, you get 7 over 5 in the first case, plus factor 2, you get 5 over 6. Now 5 and 6 don't share a common factor, so now we can perform the cross multiplication. So we have a half up front times 7 times 6 plus 5 times 5 over 5 times 6. So 7 times 6 is 42, keeping again the half up front. So we get 42 plus 5 times 5 is 25 over 5 times 6 is 30 equal, well, 42 plus 25 is 67. And if we multiply on the bottom, 2 times 30 is 60. Now this may not seem like much, but it was only really because the factor was rather small. If you're adding fractions and the denominators share more than one common factor or a larger common factor, what's going to happen is when you perform here the multiplication, it will artificially inflate the numbers you're dealing with. You see here, by factoring the 1/2 right away, we had to perform 42 plus 25. But without factoring the common factor on the denominator, we had to perform 84 plus 50, right? Those numbers were twice as big as those ones. But what if we had, say, a common factor of 45 on the bottom? Then those would have been 40 times larger than those two. So the point is, whenever you're adding up fractions, before performing the cross multiplication, always look for common factors in B and D, and if there are any, factor them out, and this will lead to a simpler solution by keeping the integers as small as possible on the numerator. And that's it.